Hello there, and welcome to another ClueCon Weekly. Every week we come along and get a guest in the studio and bring you an interesting person talking about something very interesting, or maybe many things that are very interesting. And this week is no exception. We're very pleased to have James Tagg, a veteran of ClueCon, along in the studio today. How are you doing, James?
I'm pretty good here. I'm in San Diego, so been locked at home for the last 20 odd days.
There are worse places to be than San Diego, James, aren't there?
Yeah, it's a great place to hunker down. Correct.
Good. Well, thank you for taking time out and for coming along. I've seen you at various events, including ClueCon, and you're generally speaking when you come along to ClueCon. What have you been up to recently?
I've been working on two things. There are things that I've described at ClueCon conferences before, so it's been quite a long project, I guess. Well, startups are always long projects. The average time I've spent on startups, and I've only done so they take a long time. All startups make their sort of money starting year 7. So startups are a long process. The idea that you raise some money and you knock out a startup and 2 years later you sell it for several billion. It does happen, but that is absolutely not the norm. So it's like all of the other fictions. Startups are all started by 22-year-olds. No, the average startup is started by a 52-year-old.
No?
It's just not true. All the stuff that you read.
That's giving me hope, yeah. James. 52.
Yeah. So at least half the viewers are suddenly perked up, right?
That's right. Now, I first came across you when you were the Truphone man. So, for those that might have not met you before, can you talk us through, how you got into Truphone? Because was that your entry to VoIP, or had you been involved in VoIP before then?
Well, the first startup I did was straight out of college. That was a startup called Moonstone, and we developed capacitive technology, right? And we used it for a whole bunch of things. So the first thing we used it for was measuring the moisture in your wall to tell whether you had rising damp, which is a common problem in England, but not really in America. And then we used that for making weighing scales, which didn't really work very well, but it was very interesting. And then we used that for a reversing sensor for a car, which didn't really work very well because, unfortunately, certain objects are invisible for capacitance. And then we used it for making a touchscreen. And of course, touchscreen, it's perfect because you don't want it to be affected by the material of your body when you put your phone in your pocket. You only want it to detect your finger. And so actually it turns out capacitance is the best way of detecting touch on a touchscreen. And so we were the first people to make a planar capacitive touchscreen. And now, of course, everything in the world is a capacitive touchscreen. So everyone's got them in their pockets now. So that's my background. And I made a bit of money out of that startup, and I used that startup to start Truphone. And Truphone was the first company to make a VoIP call on a mobile phone.
Great
so
stuff.
That's my short potted history of startups.
Thank you. And so then, if you continue that story and take us from Truphone until what you're doing today, and then we can get on to your current project, if you like.
Yeah. So I got fascinated by this question of whether the human brain is a computer some years ago, and I spent probably a decade of my life researching it and writing a book. And then that led to basically 2 companies. So one company is, can I make a hybrid between human intelligence and artificial intelligence? It's clearly artificial intelligence is good at some things, computers are good at something, humans are good at some things. So can I blend the 2 together? So I have a company making digital humans, which are in fact a blend between human and artificial intelligence. And I'll show you, some progress on that. It's starting to get pretty. And then The other thing, of course, I did was if you think that humans are not computers, then what on earth are they, right? They have to be some sort of different type of machine or device or thing. But you then are, you're either then a mystic, sort of a, we can never explain this. It's beyond, it's beyond understanding, and so on. And lots of people have that view, right? That you just can't understand the human brain. You'd be mad to even try. But alternatively, you could say, well, okay, it's not a computer. It's a different sort of device. Let's go and try and build one. And so I'm in the process of building a quantum gravity computer at the moment. So I will. Now, Anthony always likes me to give a talk which causes people's brains to melt. And so I'll start off with some slides about digital humans, which is quite fun and straightforward. And then I'll go on to quantum gravity computing, and hopefully we'll get a few melting brains out of that.
Okay, all right, that sounds good. I'll pop us into slideshow mode, James, so you can take it away.
Yeah.
Here we go.
Okay, so I'm building digital human beings, and the motivation, as I said, to this was that we seem to think differently to brains. And the quickest way to explain this, well, a slow way to explain it, is this is a chess position which we put out in a newspaper. Humans look at this and can instantly understand it. Machines can't. Let me give you an easier visualization. Okay, so we look at pictures now, and with artificial intelligence are extremely good classifiers. They can tell the difference between cats and cheetahs in images, and they can actually do a better job than you and I now. They are more accurate, which begs the question, how on earth do you make a way of testing testing that program? And basically you show the images to 100 humans, and 100 humans will do better than a machine. But a single machine can do a better job than a single human.
Okay,
but you can take that single machine that has been programmed, that has learnt to do a really good job of analyzing things, and then say, let me show you some things. What do you think they are? And with 99.999% confidence, these images are recognized as an obelisk and a comic book and a clock and a phone and a screwdriver. So what you sort of see with computers is they have no clue what they're doing. They don't understand, right? You and I look at, the top left one, obelisk. No, it's not an obelisk. Or the top right one, a dial telephone. No, it's not a dial telephone. I don't know what it is, but it's certainly not one, right? But the computers have got this sort of algorithm that's looking for some sort of structure in the image. And if you can trick them within sufficiently little structure, then they get it wrong, right? So this is why we think that humans do something different. And just to give you sort of some level of ridiculousness, right? Here's a universal Turing machine tattooed in someone's leg. Like, this machine is equivalent to every other computer we have on the planet. And we currently believe that this simplistic machine explains the human brain, right? It seems to me fairly obvious that it doesn't. It is absolutely the assumption at the moment in the scientific community that this is correct, that this simple universal Turing machine explains all that is human thought. Why is that? Why is that kind of philosophically important? Well, computers are getting faster and faster and faster. How quickly will it be before they overtake us? So by my calculations, in 2053, a computer will have the same power as the human brain.
In terms of raw power, or in terms of
raw power, gate count,
the ability to think.
This is gate count, right? It will have as many gates in it as we have neurons in our brain.
Right.
It's taking Moore's law and doubling. Now, there's an argument also that our brain is a quantum computer, and that's slowly gaining some ground. we used to assume that there were no quantum effects in biology at all, right? Now we know that there are some quantum effects, so that photosynthesis is a quantum effect, and we think that certain bird navigation uses a quantum compass that's built into the bird's head, and that they use this quantum compass to navigate. There are two compasses that have evolved in birds. One is it's literally a compass, right? They basically grow an iron filing in their brain, and that iron filing twists. And they have a sensor in their brain that can feel the twist on the iron filing. And if they're flying north, they feel no twist. So they can fly north. I mean, it's amazing that that evolved, right? But there's also a quantum compass where there's basically a ring effect, and the bird detects this and uses this technique to find it. So we're now finding some kind of quantum stuff in biology, but quantum effects don't help, right? If your brain is a quantum computer, it just means it might have some more complexity in it, and that just means that Moore's law will take until about 2080 for parity to be reached. So by the end of this century, if the brain is a classic, is a Turing machine, computers will be faster and better at it. Well, they'll be faster, and then we'll have some software to build for them to be better. But we can already see that with what we have today, we are better at making a classifier for cats and llamas, and we are better at playing chess, and we're better at playing Go. And in fact, a computer can beat us at almost every game now, just with the power they have today. So imagine what they could do with as much power as we have in terms of gate count.
Yes, I guess the game thing is because you give them a set of rules, and then they've got the infinite not infinite, but the processing power to work out those rules.
That's right. So most games are finite. Chess has got 10 to the 41 different permutations of games that you could play, which is a lot, but it is relatively finite, and you can put a machine on it, and you can compute it. There are some things which we'll talk about later that you can't compute. Right, so there are things computers can't do. The question is whether that matters. So anyway, I am building a virtual human. Now let me flip forward a couple of slides and explain why. So the problem, I guess, is that there's an aging population, basically in Japan, Korea, USA, and Europe. In Asia, India will have half the working population in Asia by 2030. So you want to be able to send those people out to work in other countries that are lacking in labor. They have a labor shortfall. Even China is going to start having an aging population, and that's driven by the one-child policy. So the average age of Chinese is actually rising quite rapidly.
Right, although they have, when I say reverse that, I don't know whether reverse is the right word.
They reversed the policy.
But they've upped the limit, haven't they?
Yeah, but that's a 50-year policy, right? It's a 60-year policy. These demographic policies, you do something, and 50 years later or 20 years later, you start to see the differences.
Understood.
Yeah, so yes, they've started to relax the one-child policy, because their population is no longer exploding, which it was doing. But the demographics that's a result are there. So basically you have two ways of dealing with this problem. One is you put people in an airplane and you ship them somewhere. Now, before COVID, that was a pretty normal thing to do. I think after COVID, that people will be very resistant to assuming that putting people on an airplane is the right way to solve problems. The other way is you project a real human around the world, and in our case, we blend them with some artificial intelligence. So how good can you get a front end to a human? So this video is...
Hello, I'm Siren, and I'm a digital human. I was created by an international team of artists and engineers who wanted to challenge our ideas of what is...
Okay, so that is rendered in real time. Digital Human, that's built on Unreal Engine, which is the gaming platform that that Epic Games built. So that's what Fortnite is built. This is our current one, which we're working on. He'll get some hair soon, and he'll start to look a little bit less like a hitman. We call him the hitman at the moment. Yeah. So we can, with this, put people in India. So here's our team of people in India. So there's about 500 people. About 6 hours drive from Bangalore, which means it's not that far. As you know, in India, traveling by car can take an inordinate amount of time. And we allow those people to run an avatar remotely. The avatar will run off AI unless the AI is sort of faltering, and then humans can step in and puppet it remotely. And they really can. I'm just going to flip around here. They really can puppet it remotely. So here's us puppeting our demo remotely.
Talk, Will. Say some words. This took a really long time, but I finally did it.
Yeah.
And now it's working. And connected. What do you think?
Yeah, and then it's basically recognizes Will's face.
So you...
Fascinating stuff.
Yeah, and a few. I mean, people who are into this say, "Well, what else have you got around?" Let's show you one or two other things. Now, sometimes this is a Vimeo video, so it flips out. You still got my screen there?
Yes. Yeah, still got your screen.
Okay. So these are all digital humans, right? These are not real humans.
Get around, Jess.
This is a cutscene from Call of Duty built by Remington Steele.
You treat your men like you would your own beloved sons, and they'll follow you into the deepest valley. I lost myself.
Yeah, and for a bit of fun, have people seen some of these other things? Have you seen Obama deepfake?
No, I've personally not.
Which our enemies can make it look like anyone is saying anything at any point in time.
Yeah. So you see that the technology for digital human beings at the moment is really going wild.
Yeah, amazing.
I won't keep going on that. I've got a funny binging in the background.
Yeah, that's entirely my fault, and I'm just trying to turn it off.
Yeah. Let's get rid of these.
It's best if I just close that. So. Okay, all right. Do continue, James. I think I've got rid of those bings.
Okay. So you can see that I don't quite know why I've not got full screen anymore.
I can. Do you want the full screen for your screen share, or do you want it to come back?
My screen share has dropped out of presenter mode, I guess.
Yes, I think that's what's happened.
Although it's not entirely. Well, let me exit and re-enter presenter mode, and then it will grab the screen again. Okay. Did that work?
Let's have a look. Yes. Yeah. Okay. Do continue.
Right. So what we do basically is we have a customer, talks to the avatar. So they're talking to, a real-time human being. They might be doing some sort of health application, asking questions about, what do I do if I have this symptom and so on. And we then have we then have an AI that answers them, a bunch of people in India that can override the AI if it doesn't work, and if they override the AI, they record some new information. So they actually record a full body recording. So we have people in simple motion capture suits, facial capture, and so on. So then after a period of time, we end up with a whole bunch of text that has been rendered by real humans, and we can apply AI to it so that we can render the thing automatically. So we're moving from puppeting the AI, so having a human control the AI, to the AI largely working on its own. And to a large extent, what we've built over the last 2.5, 3 years is a system that captures that all in real time and allows it to teach the AI in real time. So that at least once a night, we can rerun the AI training and retrain the AI. And then the humans the next day see what it gets right and what it gets wrong and improve it on a day-by-day basis. And we're using that for a bunch of things. So there are a few business models. The ones that we're working on the most at the moment are building an educator. So we'll teach using this AI, human AI hybrid, and we're building a therapist that will mind someone who has dementia or some sort of mental problem. And that's just minding, so that's just talking to you. There's no medical intervention level skill in that. But over time, it'll get better and better. And over time, we'll put some medical intervention skill into it. So it actually becomes a trained therapist.
Yes, once you've got the mechanism there, it's just a case of kind of loading up the appropriate data.
Yes, it's loading up the appropriate data and working out what the business model is. So I'm unfortunately at the moment still in the mousetrap part of being a startup. So I'm trying to build a better mousetrap and hope that they will come. Now I'm not quite as bad as that, but that is where I am at the moment, which is concentrating on the technology side. I do have now some people who are concentrating on the business side, which is great, who've invested a small amount of money into me, and they're basically saying, James, this is fantastic technology, but you're not thinking at all about the market and things like that. So, well, no, I'm not. Because I can spend hours and hours and hours with Excel spreadsheets modeling the market and so on. Doesn't build you any technology, right? Doesn't get you anything. So at some point, you just have to go be technical for a period of time. So that's what I'm doing. So in another week or two, we used to have our old version up, which was a very poor quality visual character and some AI behind it. We've done root and branch surgery on that and put in a completely new AI system and a new visualization system. And we'll be plugging that in probably with FreeSwitch. Hopefully, I'll need some help with that, so that you can get to it over FreeSwitch. So it's basically FreeSwitch front end goes to an Unreal stack. Unreal stack renders the character. Back end connects to an AI system that tells the thing what to say, and then humans in the loop watch it and sort of improve it in near real time. Actually, they can improve it in real time, but I don't wish to say real time because then as soon as you say that, half the discussion with the financier is an argument about what real time means. Is FreeSwitch real time? No, it takes 150 milliseconds to move the packets around, or 15 on a good day, right? It's super fast, but there is no such thing as a real time. Well, the universe, of course, is real time, but then that's a conversation we're going to have next.
Yeah, very interesting point, and I can see that what you're doing. Every kind of development is an iterative process, but things that involve speech recognition and things like that, they seem even more iterative than other projects.
It's an enormous plumbing exercise, really. So you're plumbing because of the open source movement. I mean, when Anthony started FreeSwitch, which became SignalWire, 20 years ago, 16, a long time anyway.
2005,
There was quite a bit of open source around, but not huge amounts, and there was a real gap between people who did open source and people who didn't. Well, now almost everything's open source, so every piece of AI that Google or Facebook or Twitter or whatever do, they almost always open source it, and so you can simply plug it in to a system like this and build a system by mashing up the best bits of open source. So that's kind of what we're doing.
Great stuff, James. Well, thanks for sharing that with us.
So I'm just going to go and talk to you about the next bit of what I'm doing. So we think, so at the moment I've got a computer, basically a computerized AI doing the AI bit. But what I'd really like to do is to have something that could do a very good job of it. And I think that's going to be a computer. So I'm at the moment building a non-computing device. So if you look at computation, then there are easy things that you can do. This is basically the complexity zoo. So
sorry, you said a non-computing device, was it that you said?
Yeah, a non-computing device.
Okay, sorry, I missed that. Do continue.
You can't call a non-computer a computer because it's an oxymoron. So there are problems that we have, and they get harder and harder. So everyone knows this concept of NP, NP complete problems. So there are problems like the traveling salesman problem that are very, very hard to do. And did you stop to think whether NP is the hardest problem? And the answer is no. There are some problems that are harder than NP, and you can see them here in this graph. There's some slightly harder problems than NP. And then there are problems.
Let me stop you again. Sorry, I took your screen share, so let me put you back on screen share.
Oh, yeah.
Okay. Yeah, there we are. Yeah, we've got your...
So there are easy problems, right? Adding two numbers, easy, right? You can just do it straightforwardly. There are complicated problems like traveling salesman problem. They are NP complete problems. But there are problems that are harder, okay, than NP complete. There are some games that are harder and so on in game theory. And then there are problems that you cannot compute. So the most obvious, or the famous one, is the halting problem. So you can't tell whether a program will halt or not. And because of that, there are a whole bunch of things you can't do, and that's called Rice's theorem. So any non-trivial feature of a computer program is not computable. So you cannot tell whether a variable will ever be accessed, you cannot tell whether a program will ever not crash or run out of memory. All these things can't be computed. And I wrote a paper some time ago, which of course was completely ignored by anybody, that said, well, because of this problem, humans solve problems like Fermat's last theorem, which a machine should not be able to solve. And therefore, I think humans are different to machines. So I certainly felt that I could prove it to myself. Whether I can prove it to anyone else is another matter. And I'm not going to try and do that now. But I don't care, right? I don't care, because I'm not an academic that works in a university that needs to publish things and have other people accept what they say. I'm an engineer, so I can simply go out and build something. So what I'm now doing is I'm going to go and build one of these machines. So I'm going to try and build a type of computer that is more powerful than a quantum computer. And why do we want to do that? Well, there are some things that we think a quantum computer could not do. So firstly, if the human brain is a quantum gravity computer, if you want to model it, you need one of those. You need a quantum gravity computer to do it. if you think that the universe evolves in a non-computational way, and I do for a bunch of philosophical reasons, then you need one of these computers to model basic physics. It turns out that one of these machines would be able to do theorem proving, which is this Fermat's last theorem problem, would be able to prove theorems where a computer can't do theorem proving. Highly contentious. Lots of people believe that my statement is wrong, but I'm making the argument that it's right. And then, of course, encryption is adversarial. If I've got a computer that's more powerful than your computer, I can break your encryption, and I can encrypt in a way that you cannot break mine. It's just a simple arms race. So there's a bunch of reasons why one of these computers would be interesting, not least that the world has an insatiable appetite for computing. Go on.
Can I jump in with a quick question for a moment, James?
Yeah.
And that is on the previous slide. It talked about modelling the human brain. I just wanted to ask: is that in terms of input and output, or is it in terms of the actual mechanics of the brain? Are you seeking to recreate a neural array, or are you just seeking to create the kind of the output that you get from learning inputs?
I'm trying to model the brain properly. So let me explain what I mean by that. I can model an aeroplane in Microsoft's Flight Simulator. And what I do is I simply say this plane can go up and down at a certain rate and pitch and yaw at a certain rate. And I make a picture of the aeroplane, and then I give you some controls to it. And you can fly it, right? Now that is a model of flight. It's a model of an aeroplane, but it has nothing to do with how an aeroplane flies.
Right.
I've simply said this is what an aeroplane can do in terms of inputs and output. I move the joystick and the plane goes right. The other way I could model an aeroplane is I could do a finite element analysis model of the air, the fluids flowing over the aeroplane. Now, if I do that, my model is quite faithful to the physics, the reason why your aeroplane is working. So, but of course, I'm not building an aeroplane there, right? I don't have any metal in my computer. I don't have any air in my computer. I don't have, don't have a real model. And of course, what we do with airplanes, we do make real models out of balsa wood and put them into wind tunnels. In fact, NASA makes full-size models of everything it sends up and puts it into the largest wind tunnel in the world. Right? So I am making a model which is much closer, or at the end of the spectrum, where it's trying to model the actual physics to model the brain. But I'm not making neurons. Actually, I am making neurons, but I'm making the neurons out of plastic rather than living tissue. So it's quite. I'm trying to be quite faithful, and because I'm trying to be quite faithful, I think the things that you would understand from the model would give you insight into what's happening in the human brain. So why do we need it? Well, we like computing power. We all like computing power. I just went and bought a new 2080 desktop yesterday because I'd run out of computing power on my Mac. There's some theory about quantum gravity computers that we're basing it on. And what we're sort of constructing is a physical device where we have particles that are suspended in a matrix, and it's you've seen quantum computers. They're basically low temperature aluminium disks that are excited by radio frequency. So we're building a physical device, but our device, the quantum elements float. And so the quantum elements don't have a fixed position in space-time, and therefore we can use that fact that they don't have a fixed position in space-time to give us a bit more flexibility.
Right.
and it should be able to do. Actually, why don't I explain what's going on? So imagine that you are trying to model a new drug, okay? And you have some sort of protein, and you have some sort of drug that's coming towards it, okay? And this drug is going to lock into this protein. And when it locks to this protein, the protein it locked into changes shape, and it changes its behavior in that some way. That's basically how this process works, okay? So you have, a protein, you have a drug, it locks into it, it bends the protein now works in a different way. If the protein was something you didn't like, you ideally want that way that protein was flexed to cause it to stop doing what it was doing, stop replicating, for example, if it's a virus. If you get a really good protein that comes in here and it locks into here and it bends this thing, it actually can snap the protein in half, right? So you snap it in half. Okay. So this protein that's going to come and lock into this, it's sitting in a bath of water. I mean, basically our bodies are full of water. Okay, and it's going to come in here and it's going to lock into this. How does it lock into this? Well, what happens is it forms a quantum calculation. Okay, and it finds the lowest energy point that it can lock into, and it locks into that point. When we say lock into, what do we mean by that? Okay, how do you decide if a quantum calculation has finished? This is a question for you. How do you decide a quantum calculation has ended?
You've put me right on the spot, James, and I don't have an answer for you, I'm afraid.
Okay, you make a measurement, right? You make a measurement and you see whether the thing has done it. So with a quantum computer, the quantum computer runs its quantum computation, and then you press a big button and say, right, give me the answer. And it gives you the answer to the calculation you asked it to do. And you usually do that 1,000 times. And then you average the answers it gives you. And the one that gives you the most often is the answer to your calculation. That's how you use quantum computers to break encryption or do any of the things they do. Okay?
Right.
But this protein here, right, this drug that we have, came and locked into this protein, right? Who's the observer?
Who's the observer of that
who's
process?
making the measurement? Where's the measurement being made?
I guess no one.
Right, no one's making the measurement. So how does that work? So this is the great puzzle in physics, which is we see things happening, right? We see things happening in drugs. We think that this dance by which the protein finds its best fit is essentially a sort of a quantum random walk process by which it kind of comes here. If it was classical, what would happen is the water would be bouncing this around, it would bounce around, it would move in, and it would find its position. If it's quantum, what happens is the water molecules that are hitting it, Brownian motion, cause this to be in a superposition of every possibility. So when it comes to dock, everything is simultaneously tested and it finds the best position. So you should find that if you have a quantum process, the thing docks more quickly than a classical process, right? Because it's simultaneously testing everything.
Right.
The thing about it is, how does it decide not to just jump out and try another one, right? How does it decide, I'm done, I've made a measurement, I've decided? And so we think that's because of an interaction between quantum mechanics and general relativity, and so it has an effect. And so we can build a machine that is sensitive, that basically gives us a sensitivity to measurement.
Right.
And that's what we're building.
Okay, I've popped you back on screen share now because I did when you were doing your hands. I had
Good. And so a few years ago, I laughably thought, well, why can't I just make one of these quantum gravity computers out of little Arduino devices, or Raspberry Pis, and I can just suspend a bunch of Raspberry Pis in space-time and have them talk to each other, and I should be able to do it. I thought, well, that's completely ridiculous. And then about 5 years later, I've realized that that's actually possible to do. And so we are building that as our first prototype. So we're building an optical quantum computer where we suspend each device a long way from others, and we use quantum optics to do the calculation. Quantum optics you can go and buy from a catalog. Here's what you buy. So obviously this is a SketchUp, and this is actually what you buy to do it. But you build yourself a quantum device out of quantum optics on a bench, and you run the experiment. And
the point of the quantum optics is the speed of communication, is it?
Oh, it's very complicated.
Oh, okay.
And here's why it's very complicated. I want to do a quantum computation. And I want to do a quantum computation where it matters to me how far the thing is apart and how much mass is involved. So there's an experiment that you do, which is the Mach-Zehnder experiment. There are two types of experiments you do to do quantum mechanics: the double slit experiment and the Mach-Zehnder. So in a Mach-Zehnder, what you do is you take a light source and you put it into a half-solid mirror. And so the photon hits the half-solid mirror and splits, and some of it, part of it goes up and part of it goes to the right. And the question then in your mind is this sort of a decision that's made at the mirror, or does the photon go in both directions? And it turns out that the photon goes in both directions. So the photon actually splits itself into two, and part of it goes north and part of it goes west, and that's its wave function gets split. So what we're doing in our quantum gravity computers, we split the wave function so that part of the photon goes in one direction, part of the photon goes in the other direction, and then we do a quantum computation on each part of the photon without moving too much mass. And then we send a new photon on its way to the next quantum computation based on that. So we're building a quantum computation which is optical and split up. Now, anyone who knows anything about quantum computing will tell you that my machine cannot work, right? It's completely and utterly stupid, because as soon as, so what I'm building is a digital mirror, right? So as soon as the photon comes up to this black box, which I claim to be able to do something, and carries on, I'm making a measurement. And as soon as I make a measurement, it collapses to classical. I'm no longer doing quantum computing. Right? And so I'm relying on this Penrose-Diossi thing to say, well, if I can keep the amount of mass below a certain limit, I can fiddle with this quantum, with this photon without causing a problem. And this is Schrodinger's cat. You remember Schrodinger's cat?
I do. I remember the name.
Okay, Schrodinger's cat.
Knowing whether it's dead or not, isn't it?
That's right. So Schrodinger's cat it's a sort of nasty thought experiment. So he originally did it with basically a Geiger counter. The decay of radioactive elements is random. It's quantum. So it's completely random when a particle comes out or not. And so we could have most people now do it with a photon, right? So we say, okay, we have a photon that comes and it splits. And some of it goes north and some of it goes west. And we have a cat up there that sees the photon. If it sees the photon, it dies. And if it doesn't see the photon, it lives. Well, the problem is that our photon actually goes in both directions. Half the photon goes up and half the photon goes to the right. So is the cat half dead and half alive? You know, so you have this kind of weird thing where the cat is half dead and alive. And that's Schrodinger pointed this out as a thought experiment that said it's ridiculous. Quantum mechanics can't work this way. Well, it turns out quantum mechanics does appear to work that way. You do get a simultaneously half alive and half-dead cat. But we never, ever, ever see cats that are half alive and half dead. We only see one or the other. So this is the big puzzle in physics. But what quantum computers do is they rely on the fact that if you just use single photons, single electrons, single atoms, they do go into superposition, right? You can actually look at them and see that they're actually in both states at the same time. We never see cats, but we do see photons and atoms. And so a quantum computer uses this fact that small particles can go into superposition, and we can therefore compute with them. The question is, can we compute with quite large things in superposition? And so what I'm doing is computing with quite large things in superposition, i.e. little Arduino computers. So that's what I'm doing. And I won't go through all the slides to show you how that works and how the experiment works. But at the other end of things, we think that this might be what happens in the brain, and that there's structures in the brain that use the same technique. And the structure that we think is most likely is this one.
Now,
So
I can't see your mouse pointer at the moment, but I'm
okay. So where you can see a video, right?
Oh yes, I can now. Sorry, I was perhaps a little bit behind.
See a video. Okay, we're gonna. All right. So this is inside the brain. So this is actually inside a neuron. And inside the neuron, you have all these fibers, and these fibers are. There are two types of fibers: actin and tubulin. And these fibers basically hold your neuron together. And they're quite sophisticated. So when your cells divide, these fibers move around, grab hold of the DNA in your cell and rip it in half. And then there's a process by which some other things come along and repair it so that it becomes DNA again, a double helix rather than a single helix. So these fibers are very intelligent, or something's intelligent enough to cause these fibers to be able to move around and rip a piece of DNA apart correctly so that we duplicate the cell. And this shows you just how complicated the processes are in the neurons. So you might think neurons are just very simple things, which are like a piece of wire. You know, everyone thinks of them as a piece of wire. This is subcellular intelligence, right? This little kinesin motor, right? He walks along the microtubule, carrying some stuff that was synthesized in the central part of your neuron to the other end, so that the other end gets some energy or food and so on.
Fascinating.
Right? So it is not true that at a subcellular level, neurons are boring bits of wire. They're incredibly complicated, and they have some degree of intelligence in that these things know where to go, right? And how much to take there, and what to bring back, and so on, right?
And how did that intelligence get there in the first place?
Well, either a god designed us, or it evolved, right? I'm definitely on the evolution side, but for this purpose, I don't need to get into religion at all. I can just say it is astonishingly complicated, astonishingly complicated, right? And we should just be in awe of it, regardless of what our philosophy is. We should just be in awe of it. And it's way more complicated than the sort of simplistic models that we look at. And so this is what I meant by making a model earlier. I'm doing something where I'm trying to simulate some of this subcellular intelligence as part of my computer. And hopefully, therefore, some of the good and bad things that we see our brains doing will be exhibited by the device I make, and we can then do things to that device to make it, better if it's doing something bad. And the obvious one is migraine and seizures, which I think are a computational failing of our brains.
Earlier on, James, you said when you were talking about startups, you said that I think you said the average one that's successful takes 7 years. Are you sure you're going to be able to fit this in for 7 years?
Into my life? I think I have just enough time, yeah. I have just about enough time, I think, to do this. I mean, obviously, the Send Digital Human is a bit more linear. You know, I can get that up and running quite quickly. But we are building a quantum gravity device and software that runs that, so that we can actually build a digital human that thinks and speaks like we do, rather than thinks and speaks like a machine. That's the end goal.
Right. I've popped you back on the dual screen with me.
That's my last slide. I'm done. Hopefully, I've caused a few brains to explode. Some mathematicians will be foaming at the mouth at this time, going, "No, you can't do this, James. This is completely ridiculous."
Well, you've certainly melted a bit of my brain, James. I don't know where it's disappeared to, actually.
Yeah. Oh, and that picture of your brain is a bit inaccurate. It's a very pretty picture. Your brain is more like swimming in kelp, which is why this image is up on the screen. Everything in your brain is very furry.
Okay, I've just popped your screen up.
Everything in your brain is furry. It has lots of little filaments coming out of it. The thing is, when you do diffraction imaging of your brain to see proteins, the furriness doesn't appear, because X-ray diffraction sees crystalline structures. So DNA is a crystalline structure. Microtubules and actin are crystalline, but microtubules are crystalline with fur. So you see the crystalline part, you don't see the fur. And so at the moment, my theory is that where the brain is doing this interesting thinking is in the furry part. It's in the bit that we can't image today.
Right.
We know the fur is there because we can take tubulin and we can sequence it. We can put it into a molecular sequencer, and we can get out its protein structure, and then we can say, well, I've got this protein, and it folds like this, and it's got a bit of fur that sticks out. I know there's fur there, but when I do imaging, I can't see it.
It's all very fascinating stuff. We're coming towards the end of our time together, and I hesitate to ask this question because it could give us another half an hour or an hour's worth. But
only half an hour, an hour.
very, very briefly, just on the way that things are remembered. Are you a believer, having done what you've done, that the memory is contained in the brain, or do you think the memory stretches out across the whole cellular structure of the body?
It's predominantly in the brain, but something like 10% of your neurons are not in your brain. You have a significant number in your gut, your heart, and other places. And so it's perfectly possible that some degree of computation is occurring across your whole body that you are sensitive to. But I mean, unfortunately, we've done the experiment, haven't we? I mean, that Superman fell off his horse and broke his neck, right? He was still obviously, the same person. He just no longer had any nerves to his gut, the rest of his body, and so on. And so, couldn't do that. But we know that people who sever their spine quite high up, right, they don't live past 40, right? So clearly, the brain-body nervous interaction is really important to the way the body works. We are telling the chemistry of our body what to do, and probably the neurons in the rest of our body are telling us interesting things. But the idea that our emotions are in our heart and so on, and we have gut instincts and things like that, there are people who strongly believe that a large amount of our intelligence is spread across our whole body. I think it's it's not likely. I think most of it's up here, but a little bit could be spread out. And there are animals that are completely distributed, like octopuses, right? Who do have a distributed brain.
Yes, the basis of my question was really I heard somebody speaking some time ago, and I forget where or when, and they were relating a story, and it is only a story, it's not
the heart transplant one.
That's right. It was about the heart transplant and the guy who received it becoming, was it better at chess or something like that? There was some like improvement in his abilities in a certain area.
I've heard anecdotally those things, and of course it's a viral meme that's likely to spread because it sounds so cool that everyone's going to tell other people this story, regardless of whether the story is completely made up bunk or in fact true. But I've heard the story from multiple routes. I think it's unlikely. I think it's probably just a story, but there are a significant number of neurons in your heart, and those neurons will have memory, and you are moving a device from one body to another body that has memory in it. Right? I just don't think that you store chess in your heart. I think it would be a very, very inefficient way of trying to play chess. But to the extent that you might have some feeling that a chess move is a good or a bad move, and that you could entail other parts of your body in that calculation, in that gut feeling, it's not out of the question. But the story I heard was that so I could sort of vaguely believe that you could get better at chess because all the processing is in your brain, but the sort of gut feeling might be a bit spread out. So you might acquire some slightly higher or slightly low risk tolerance by having a different heart, because your heart speeds up when you get stressed. You got a different heart that speeds up in a different way, you'll have a different stress response. If you're less sensitive now to stress because you've got a different heart that's saying, I'm quite happy to beat faster without telling you that's a problem, I might bungee jump. I might play that chess move that I wouldn't otherwise have played, right? So I can believe that in something like that, it could have an effect. But the one that I heard was that a transplant from a dancer and the person could then dance. I think it's a story. Honestly, I think it's a story.
There's a few variants out there, doesn't it?
Yeah, I've heard the story many times with different twists. I think it's a story.
Okay. Well, James, thank you very, very much for coming along. You've given everybody a huge amount to think about. We can see your email address at the bottom of your video feed there. But if people want to know more about what you're up to, where can they go and look? Have you got an online presence?
There's a few online things for me. They're all a bit sort of behind the times at the moment because we're doing technical root and branch surgery. But I'll try and update things sort of soon. But otherwise, email me, and there's decks for all companies. There's white papers with all the papers linked to them. There's lots and lots of detailed material, but certainly the Valis quantum gravity computer is still pretty much stealth. The website just says we're doing something cool, email us, and the Sen website is quite old, so you've seen what we're actually doing. None of that is public yet.
Okay, all right. Well, we've got at least a means of contacting you.
Yeah.
So, James, thank you very much for coming along and spending some time with us. Thoroughly enjoyed it, and look forward to seeing you again soon, wherever that might be.
Yeah. Okay. Great. Hope to see you in Chicago when things get good.
Yeah, me too. All right. All the best, James. Thanks for coming along.
Bye.
Bye-bye.